Okay, good afternoon. We're continuing our discussion of the OJA learning rule. I'm not sure that I used this title last week, but I'll remind you that we saw that for information transmission, if you have one neuron which is receiving input from n neurons, and you want to choose a dimension by the weights, you want to choose to project the input into one direction, from the point of view of information transmission, you want to choose the first principal component of which depends on the statistics of the inputs. And what we're doing now is I'm going to argue that there is a simple biological learning rule that will teach the weights, the connections between this neuron and its inputs, to select this particular direction in the n-dimensional space. So we have our n neurons, or n inputs, which I'm denoting by x, and I imagine a very simple, I'm looking at a very simple model of a neuron, which is just an object that sums linearly the inputs that it receives with some weight, and that generates its output. So we imagine the output of this neuron as to be simply a linear sum of the inputs. I'm already assuming that means have been subtracted, so I'm thinking about all these inputs as having zero mean. This could always be taken care of by some bias. I mean, if they didn't have zero mean, I could add some bias term here to get rid of it. And I was starting to suggest a particular rule for the dynamics of the weight. So these weights W, I think of them as representing the synaptic strength, the strength of the synaptic connections between this neuron and its input. And I was suggesting a particular rule for the update of these synaptic weights, which is based on what we know that actually happens in synapses. It's a biologically plausible rule. And let me write it down. So I imagine that after a presentation of one stimulus, the weights are related to the weights before the presentation of the stimulus by the following relationship. Okay, so this part is the normalization part. This part just ensures that after the update, the sum of the squares of the weights will be 1. So it's always kept, the sum of the squares of the weights will always be kept as 1. And you can imagine that this is kind of an idealization, a mathematical abstraction of a process which might be a bit more complicated in how it works, but it's not inconceivable to think that there is some process at work at the neuron which keeps the strength of the synaptic weights going into the neuron under control. That sums the sum of the squares of the synaptic weight. So this is what this term is doing. This is the Hebbian learning, because you see that the change in the strength of a synapse is proportional to the product of the activity of the neuron and the activity of the presynaptic neuron. So this is the usual idea about Hebbian learning, that a particular weight is strengthened if the postsynaptic and presynaptic neuron are coactive. And eta is a parameter which controls how fast the learning is, how fast is the learning. So eta, we'll call it the learning rate. Yes, and of course this is also just for the ease of the mathematical treatment. We don't imagine that everything is happening in very precise, discrete steps. Okay, and now what I want to explore is what are the consequences of this learning rule. So the first thing that I'm going to assume is that eta is small. And if eta is small, I can expand this expression to first order in eta. Take the first term in the first two terms in the Taylor expansion. So let's first write down the first order expansion of the 1 over the denominator. So 1 over square root sum over j wjn plus eta yn xjn squared is equal to 1 over square root. So I will expand the squares and take only the first order term in eta, because I'm going to throw away everything which is eta square or larger. So this is going to be sum over j wjn squared plus eta times, now I have a 2, right, because of the product, 2 sum over j wjn xjn. Now this is already 1 because in the previous step there was a normalization of all the weights, of the squares of all the weights. So I have here 1, square root of 1 plus 2 times something. And do you remember what is the Taylor expansion of 1 over square 1 plus eta times something small? So to leading order in eta, when eta is 0, this is simply 1 divided by 1. So this we have here 1. And what would I need to write here? So what is 1 over square root of 1 minus x, or 1 plus x when x is small? Yes? Mm-hmm.
You summed over Wn and xjn also, but you have another xjn. Shouldn't it be squared?
I have a term which is the mixed term, which is what I wrote, and there is another term which is this thing squared.
Yeah.
But this thing squared is of order eta squared.
So the mixed term is twice eta times y times x, right? And you wrote.
Oh, there's a y missing here, I think.
Yeah.
Thank you.
Or
Is that now it's okay?
Why? But why the w
Um, because it's a product of this and this.
Okay.
And this is a good opportunity to also do something else. This is y. And here we have a sum over j, wjn, xjn. But this is nothing but yn, right? So I can write everything which is written here as 2 times eta times yn squared. Okay? Now, 1 over square root of 1 plus x. This is something that all of you should remember how to do. To first order in x, this is minus half x. This is the first term in the Taylor expansion of this function. So I will replace all this by 1 minus eta times half what's written here, so it's 1 minus eta yn squared. Okay? And of course there are higher order terms in eta, but I'm neglecting them. Okay, so if we take this into account and remember that all this multiplies the numerator, then to leading order in eta, I can write that win plus 1. I mean, to leading order, it's just win. If eta is 0, then we will have here win, and here we will have 1. So we will get win. And then the first order term in eta will have two contributions, one from the numerator. So this will be eta yn xin. And then because of the denominator, when I'm taking, I mean, 1 over the denominator is this thing. This multiplies the expression that we have here. So to get something that is proportional to eta, I need to take this term multiplied by this. If I will take this term multiplied by this, I will already get eta squared, so I'm ignoring it. But this time, terms this gives me something which is order eta. So I get minus win yn squared. So we can summarize. So this was just mathematical manipulation, but we can summarize what we found, that this rule, if eta is sufficiently small, can be written as the following rule. Delta w is equal to, which is this minus this, is equal to eta y, or here let's put an index, y xi minus wi y squared. Okay, now I'm going to make another step, which is really very important, and it's important to understand the difference between the step that I'm taking now and what I've done before. Here I assume that eta is small just in order to Taylor expand this expansion. So I'm assuming that at each presentation of a stimulus, the change in W is small. Okay? Now I'm going to assume that eta is small in another sense. I'm going to call this slow learning. We imagine that at each step, x is selected from some probability distribution. So the change that will occur in W in each particular step will be some stochastic process. Each time it will be different, and it depends on the particular choice of x which was drawn. What I'm going to assume now is that the learning is sufficiently slow that this process samples the whole distribution over the inputs, which means that if eta is sufficiently small, I can say that delta W over some longer time scale, over the presentation of many, many different presentations, will be proportional to the average of these quantities averaged over the statistics of the inputs. So I'm going to replace this by the average of yx. Let's put here an I and here an I, minus the average of wi y squared. Okay? What does this mean? What does this mean that I'm assuming that the learning is sufficiently slow? So we can even write that delta wi is equal to some other parameter. Let's call it eta tilde, which is oh, you know what? So what I can write is always is that the average of delta W is equal to eta times this thing. Okay? This is true for one particular presentation. The average of this is the average of this. But now, if the change in W is sufficiently slow that W remains constant over the time scale over which we can sample the full distribution of the inputs, then I can replace this equation, which doesn't tell me about W because it's something only tells me about the mean of W over many, many different occurrences of this process. I can replace the dynamics of W by deterministic dynamics that I will write as follows. dW to dt is equal to some eta tilde, which is representing the learning rate in this continuous time description. And here I will write, so this is I, the average of y xi minus wi times the average of y squared. So again, the idea is that if the learning is sufficiently slow, that I can pick some time scale over which on one hand W is almost constant, On the other hand, over this time scale, there are many, many different presentations of the inputs. And because the learning rate is sufficiently slow, if the learning rate is sufficiently slow, there is some time scale over which many, many inputs are presented. Because many, many inputs are presented, automatically the change in W averages over the statistics. Okay? And so this time scale, again, has to be sufficiently large. There should be some time scale. The learning should be sufficiently slow that there is some such time scale over which, on one hand, the sum over the individual updates for many, many stimuli becomes very close to its mean. Okay? And on the other hand, the change in W is small so that I can treat the W that appears here as if it's constant during that time scale. If that is true, I can describe the dynamics of the weights using this deterministic equation. There's no stochasticity in this equation anymore, but I need to calculate what is the average of y xi and what is the average of y squared. Okay. So this is called Ojja's learning rule. And before we explore what it does, I want to mention that I derived it from a biological view of what could happen in a synapse, from the idea that synapses the dynamics of the synapse is governed by Hebbian learning plus some normalization over all the incoming synapse to the cell. Just a moment. But I would like to mention that this same rule can be also derived from a different standpoint, from a different viewpoint. And this is related to what you've done in the last TA session. Remember that you saw in the last TA session that the choice of the first PCA component can be motivated not only by the Infomax principle, but by a related idea, and this is that if you want to be able to reconstruct the input as accurately as possible using a linear expansion from this neuron to some outputs, and when I say as close as possible, I mean according to the sum of the squares of the difference. So you have an input, you project it to this neuron, and then you generate an n-dimensional output, and you want the sum of the squares of the output and the input to be as small as possible. So you saw that if you want to construct a network that achieves that, that tells you that you want to choose these weights as the first PCA component of the input. So it's possible to write a set of to derive the learning rule as a way to optimize the sum of the idea is that you want to optimize the sum of the squares of the differences between the input and the output, and various mathematical manipulations that I will not do here would lead to the same learning rule that I wrote here. Okay? So it can be, again, it can be, on one hand, it can be derived from some normative goal. You want to generate a set of weights which will allow you to produce the best possible reconstruction of the input, and you do this by minimizing the least square errors in some learning scheme. I'm just telling you about this. I'm not doing it in any detail. On the other hand, the learning rule that you get makes sense also from a biological standpoint. Okay, now there were some questions. Rotem. Yes. Right. So you should imagine that in each one of these steps there is a tiny change in W, right? And say there is a tiny change in one step, one presentation of stimulus, but we're really looking over a time scale, I don't know, presentation of 1,000 stimuli. And even on that time scale, I imagine that all these changes in W add up, but they're very small, okay? So to leading order in the learning rate, in eta, I should put here W. If I would take into account the fact that the W's are actually changing just in a tiny little bit each step, this would replace W here by W plus eta times something, right? But then you will get a term which is eta times eta. So this will be a term which is second order in eta. So to leading order in eta, I can treat the weights here as if they're constants during this learning. And it also makes sense. I mean, if the weights are really changing by a very, very little amount during the presentation of these 1,000 stimuli, then the change in W will be governed by this term and not by the fact that W is actually not exactly W, but W plus a little bit of change that occurred during this time. Okay, that's the idea. Make sense?
The weights are constant and there is slow learning.
Yes.
It's compared to what? Compared to change Y?
So Y changes very drastically from in each presentation. In each presentation, you have a different X and a different Y. We're averaging over the many presentations. So again, when I say that the eta is small, that the change is small, I actually mean two things. One is that in each particular presentation, the change is small. This is needed here for the Taylor expansion. But the more severe, the more important requirement is that it's not only small over the presentation of one stimulus. I assume that it's small over the presentation of many stimuli. For how many stimuli does it need to be small over, so, I don't know, 1,000 stimuli, a million stimuli? It should be small over a presentation of a large number of stimuli, which is sufficiently large such that you get a chance to sample the statistics of this expression, because I replaced here this expression, which can change wildly from one presentation to another. I replaced all this by the mean over many presentations. Okay? You don't look very completely satisfied, but the idea again is that we get a chance. The learning rule, in each presentation, the change in W can be very different, depending on what was X and what was Y. But if we're presented by I don't know, 10,000 stimuli, then all these changes will sum up, right? And then we can replace the sum over one stimulus by the mean over the presentation of many stimuli. But we're assuming that Y remains constant during this time scale, and so we need, because otherwise I would need to each time here write a different W. Okay? The change here depends on W. Right now I wrote the W, I just took W out here, and I treated it as if it's constant.
Then why do you need the expectation of the Y if you know that Y doesn't change?
No, Y changes from one stimulus to another because Y depends on which X is chosen at each step. So Y can change wildly from one presentation and the next presentation. Each time there's a different vector X drawn from the distribution of the X's, and Y can change very wildly from one presentation to the next. Okay? So this is why I need the mean over Y. I assume again that I can take a time scale over which W remains more or less constant, but the meaning of these averages are, just imagine for a moment that W was fixed, was frozen. W would not be allowed to change at all. We would still need, YX, this average, Y times XI, or this quantity, Y times XI, or the quantity Y squared varies wildly from one presentation to another, and the idea is that we average over many of these presentations. Okay? Okay. Now, the last part is that we need to see, I want to show you that these dynamics generate something interesting. I'll do this here. And so what I want to ask is the following. So here we have now a deterministic equation for W. What do I mean by this? The average, so in these averages, we treat W as if it's fixed. And of course, the average of Y squared will depend on the W's, because the Y is a function not only of the X's, but of the W. So we have a change in W, which it's not written here explicitly, but it's implicitly dependent on the W's through the fact that this average depends on the W's, this average depends on the W's, and you also have the W's explicitly in here. So there's a dependence, dW to dt depends on all the W's. And I want to ask whether these dynamics lead to some steady state, whether they converge to something, whether the weights converge. So I'm going to assume right now that the weights will converge to something, and if they do converge to something, this something should be, the steady state of the weight should be such that W stops changing. So if W reaches a steady state, what we have on the right-hand side should be 0. So let's see what that implies. If we're at a steady state, the average of y xi should be equal to wi times the average of y squared. But remember, what is y? Y is equal to sum over j wj xj. So let me put this explicitly in this expression. I have here sum over j wj xi xj. I'm putting the average only over the x's because we're imagining now that the average is over representations of the stimuli, but the W is treated as if it's fixed. Okay? And this should be equal to Wi times sum over j and k, Wi, wj, wk, xj, xk. Okay, what I've done here is that I wrote y as sum over j, wj, xj, and the other y as wrote as sum over k, wk, xk, and I just wrote this product, and I used only the average. I put the average only on the x's. Okay, what is this? This is a correlation matrix of the inputs. Describes something about the statistics of the inputs. We call this Cij, right? So what I have here is that sum over j, wj, Cij is equal to wi times sum over jk, wj, cjk, which is this thing, wk. Okay, so if the weights reach a steady state according to these dynamics, this equation should be satisfied. Let's write it as a matrix equation. This is the matrix C multiplied by the vector W, so C times W. This is W transpose CW. And here we have simply, so this is the ith component of this matrix, right? Because here you have I. And on the right-hand side, we have this number multiplied by Wi. So this is the vector W. Maybe I will put a vector sign here just to remind us that these are vectors. Okay? Now this is just a number. So what did we find? What does it mean that C times W is a number times W? It's an eigenvector, right? So this equation, without even trying to calculate anything here, tells me that the vector W, the vector of the weights, if this system has converged to a steady state, the vector of the weights is an eigenvector of the correlation matrix. So it's one of the PCA vectors, right? It's one of the principal components of the correlation matrix. Okay, so what we've seen so far, again, if these dynamics converge to a steady state, necessarily the system has chosen one of the principal components of the inputs, but we haven't shown which one. Maybe it's the first principal component, maybe it's the second principal component, maybe the third. So now I will just tell you, without showing this, but you will work on this question a little bit in the next exercise. I will just tell you that it turns out that the system will choose the first principal component, and I will explain to you why. If you want to understand into what state a dynamical system goes to, it's not sufficient just to ask whether some state is a steady state of the dynamics. what we also want to ask is whether it's a stable steady state, right? So what we've actually found here is that if W is one of the eigenvectors, one of the principal components of the dynamics, this will be a steady state, but maybe it's not a stable steady state. It turns out that if W is proportional to the first principal component, then it's possible to prove that it's a steady state, that any small perturbation in the W's will dynamically decay back to zero. However, if you choose W to be one of the other eigenvectors with a smaller eigenvalue, not the first principal component, and you introduce a small perturbation, then what happens is the following. If you introduce a small perturbation in the direction of a principal component with a principal vector with a lower eigenvalue, this perturbation will decay. But if you go in the direction of a principal vector with a higher eigenvalue, this is a perturbation which will start to increase exponentially. And it will not, so therefore it will not, this is not, if you're at an eigenvector which is not not the highest eigenvalue, this is not a stable steady state. Okay? So if there's a little bit of noise in the dynamics, even if the system, for whatever reason, reaches precisely one of the eigenvectors with a lower principal component, it will not stay there, because once the noise generates a perturbation in a direction which corresponds to a higher principal component, this perturbation will start to grow, and the system will run away from that state, and eventually it will land at the one and only stable steady state of the dynamics, which is the eigenvector with the highest principal component. And again, you will show this, you will work on this in the exercise. Okay. Any questions on this? Okay, I just want to point out that what we found here is, I think it's a very, very beautiful result, that we take some learning, some rule, which is coming from what we believe is happening at the level of the biology, the mechanism of, the mechanistics of what makes a synapse change. And we look at this very simple network. It's really one neuron connected to many inputs. And we find that if we ask what does these dynamics produce functionally, they produce something which has a functional significance, that they teach the neuron to select out of the, to linearly weigh the inputs in such a way that it's really selecting the first principal component of the inputs. I would like also to mention briefly an extension of this idea. I will not show much of the details. And this is a generalization of this idea to the case where you have more than one output. So here we had one output. You might ask whether we can extend this idea to more than one output. So imagine that we have our inputs, 1 to n, and we have m outputs. So these will be our input xi, and we'll call our outputs yi. And you've seen, we've seen previously that we might want to project, at least in the case where, that in many cases we might want to project our inputs into the m first principal components of the correlation matrix of the input. And we might ask ourselves, is there some biologically plausible learning rule that we will teach our set of m neurons to do that, to select a subspace that corresponds to the first m principal components? So there have been many works in the literature related to this question. Most of them did not look for a biologically plausible learning rule. So there are various suggestions for how to generate some learning rule of weights that will do this. But again, most of them are structured in such a way that it's difficult to see how they will be implemented biologically. So I want to focus on one principle, on one particular suggestion, which was made by Foldiak, 1989. It's not a very beautiful paper. You can see it on, not a very beautiful paper. You can see it on the Moodle, but the idea is nice. And he proposed the following. Imagine that, so let me first say actually that the most simple thing you can imagine is just connecting each one of these neurons, output neurons, individually to the inputs. But this, of course, will not do the trick, because then each one of them will converge to the first principal component, right? So we obviously need some way to make these different neurons generate different outputs. And the idea that Foldiak explored was the following. So we will have inputs going from the weights going from the inputs to each one of the neurons, as before. This will be called Wij. But we will also have recurrent connectivity between the neurons at this level. So each neuron here will be connected to all the other neurons with weights that I will call W tilde ij. And once we have these weights, all these neurons are communicating with each other, and we might hope that they will communicate with each other in such a way that will cause them to choose different directions of the inputs. And the idea that Foldiak had, which I think is quite intuitive, and it turns out that it works, is that if we apply a Hebbian learning rule for these W's, which is what we've done in the Oja learning rule, but on the other hand, for the Wij tildes, we will apply an anti-Hebbian learning rule. An anti-Hebbian learning rule wants to make different neurons uncorrelated with each other, because it increases the weights between them if they're anti-correlated. So this was the idea. Let me just first describe the dynamics of this network. The dynamics of this network is described by the fact that Yi, Yi is equal to the sum over j, going from 1 to n, Wij xj. But the activity of neuron I is dependent also on the other Yi's because of the recurrent connections, plus sum j going from 1 to m, Wij tilde yj. Before we talk about the learning rule, let's just pause for a moment and think about what this means. You see here that the Yi, if I tell you what are the x's, what are the inputs, it's not completely trivial to say what are the Yi's, because the Yi depend on the x, but they also depend on the other y's. This is the consequence of the fact that we have recurrent connections. Dynamically, you should really think about this equation as some steady state equation of more detailed dynamics that describe the dynamics of these neurons. Everyone here who took Reshatot Aleph should be able to understand what I mean by this. You might imagine that in reality, the output of the neuron is described by a little bit somewhat more complicated equations. dy to dt is equal to minus tau y, where 1 over tau y, where tau is the membrane time constant plus its inputs. And what I really mean by this equation is that after a time, say a bit longer than the synaptic and membrane time constants, the activity of the network, of this network, because now this is a recurrent network, the activity of this given the x's, the activity of this network settles on a solution of this equation. To write down the solution, we would need to solve this set of equations. So let me just write what that means. I can write y as in terms of a vector. I can write it as w times x plus w tilde times y. And this means that the unit matrix minus W tilde Y is equal to WX. And this means that Y is equal to 1 minus W tilde to the minus 1 WX, right? So really solving this equation means that we need to inverse the matrix 1 W minus W. But I will keep the description using these equations. Okay, what we defined so far is just based on this architecture and our simple model of linear neurons, what is the relationship between the output to the network and the input to the network, X, and the output of the network. Now I want to add the learning rules, the changes in the synaptic connection. So the learning rules that I'm going to apply for the W's, connections between the X and the Y, is the same rule that we saw before, the Ojja learning rule. Delta Wij is going to be equal to eta times xj y I minus wij yi square. The only difference between this and what I wrote before is that now y has its own index, right? Because we have more than one output unit. And the suggestion of Foldiak was to apply the following learning rule for the W tildes, the connections between these neurons, to be an anti-Hebbian learning rule. So the connection is strengthened if the yi, yj have opposite signs, and it's weakened if they have the same sign. You should always keep in mind that we have already imagined that we subtracted means from everything. So in reality, this might be y minus the average of y and y minus the average of yj minus the average of yj. Okay. Now, I just want to write down what are the studies if these dynamics for delta w. If these dynamics for wj and w tilde ij converge to a steady state under slow learning. It's anti-Hebbian because there's a minus sign here. So if these neurons tend to have similar behavior, this will be positive and the weight will be decreased. If the neurons tend to have opposite behavior, when one is positive, the other is negative, then the weight will increase. So this is anti-Hebbian. No, the connection is not between a neuron and itself. This connection between two neurons. But if these neurons tend to... Oh, good question. This is only for I different from J. We assume that there are no connections between a neuron and itself. So all these W tilde ij exists only for pairs of neurons where I is different from J. Okay. Now for slow dynamics, steady state, we must have that this thing is on average 0, yi, yj is equal to 0, and also this thing on average is 0. So xj yi is equal to wij yi squared. Foldiak did not treat these equations and show that they do anything. He just simulated these dynamics. And what he showed in his simulations are that once the dynamics typically does converge to something, and what it converges on is a solution for the W's and Wij's such that the relationship between the input and the output, which is written here, right? There's a linear relationship between the inputs and the output, is such that X is projected into the subspace of the first M principal components. Okay? It's not necessarily true that each one of the output units represents one particular principal component of the inputs. They can mix them. We saw that there are many different ways to do this. But the solution projects to the subspace of the first M principal components. Foldiak did not prove it. He just showed simulations. I suspect that it is possible to prove it. It's more difficult than what we've done in the case of the single output neuron, because now when we write the yi here, it's not related as simply as before to the x's. The relationship of the y to the x's is more complicated through this equation. So I didn't try to prove it, but I suspect that it is possible to prove that under certain conditions this is what happens. But I just wanted to mention the idea that you can construct, again, through some biologically plausible learning rules, you can imagine how a set of neurons learn to pick up the first M principal components of the input. Okay, let's take a break and start a new topic afterwards. מה זה? לא, כי זה וקטור וקטור. זה סקלר. כן, יש פה סכום על I ועל J, WI, CIJ, WJ. חכמנו על שניים.
okay, conjugate for
ואז שם כל איבר P, ויום טוב
זה אמור לצאת נכון, וגם זה יצא שזה לא נכון עם חלוקה ב-N,
ואז
חלוקה ב-P.
יש וקטור ה-5 וה-10, האיבר הראשון
כי
שלהם, האיבר
כי
השישי,
אנחנו
אם את משתמשת
האיבר אחד
בצורה
שלישי, האיבר
לחזור עם מסה,
זה מה שאמרה לי, אין מושג של השאלה, היא אמרה לי,
לא, לא עם התוצאות שלך, אבל עם אימא.
שזה לא נכון לכל, כאילו, שאנשים צריכים מאחד, אחד ועוד C, ולא משתיים
אני יכולה לדבר על משהו, אם זה לא משנה, זה אמור להיות ככה, כן, אני כן, כאילו, זה יותר פלוס זה אימא, כן, חלק ממנה,
כאילו זה אמור לעבוד לכל
כן, זה משהו,
כאילו
רק בשביל שתראו כאילו בעין, זה לא דבר.
אוקיי. אבל השאלה שכולם שאלו, זה מה נראה צריך לעשות בשלוש
לא, לכל אינטגרציה,
אם תוכלי מגדרים לעבור ולדבר למה הכוונה, זהו. לקחת משהו כל K במקום C, זה לא רע, כאילו לא הבנתי לא הבנתי מה
כל אחד יש לו את השאלה אחרת על מה אולי
אז הנה, באתי לשאול
לא, כאילו, אני לא הבנתי בשביל אבל
זה לא נורא.
סבבה, אני בכל זאת לכתוב את זה על הפורם, לא, משהו עקרוני, אחד על מסה, באופן כללי, נגיד שאני עושה קונבולוציה, כאילו אין לי שום דרך לראות בשביל דבר שקשה לך, נגיד אני עושה את הקונבולוציה, השאלה הזאת כאילו לראות, אני יודעת להשקיע חלק חשובים, אז עשיתי את זה דרך התחום קריאה והאינדרך, רציתי לבדוק, ורציתי לבדוק שזה נכון, אז עשיתי גם קונבולוציה בלי לעבור דרך התחומיות. עכשיו, זה לא יוצא את הדבר, אלא אם כן אני לוקחת מה שעבר דרך הפוריה ועושה את הגיל שלו. כאילו אני עושה את הגיל, אז אני מקבלת בסדר את ההקשר מהתחלה. וכאילו המסה, משהו בו לא מדויק, כאילו לקחתי נגיד, המוצאת ההופכית של מוצאת הפוריה, היא קצת דגל. נכון?
לא, אבל כאילו, הוא מבין מה זה אומר יש לך בגינה?
כן, אבל זה לא להגיד
לא, כן, אבל נגיד, רציתי לבדוק אם יש דיוק, אז עשיתי, לא, אני חושבת שתלך אייטם מכפילה אותם, אז נראה שלי צריך לנרבד ממש. אז לקחתי את המוצאים, עשיתי את זה גם שלב, כמה אכפת לי ביניהם לראות אם זה מקבל אחד. בדקתי את הטרייס של התוצאה שלי, אוקיי? לקחתי Q, דגל, אכפת לי ביניהם ובדקתי את טיפוס טרייס. אז עבור N שווה 80, אני מקבלת טרייס של 80, אבל עבור N שווה 100 ומשהו, אני כבר מקבלת I בטרייס. כאילו, זה כאילו אבל גורם לזה שכאילו כל מה שוב ולעשות שתגיל, אין פה מה לחשוב, בשום מקום אני לא יכולה לראות שמה שיוצא לי כאילו תמיד אני נשארת עם זבל של הממוקף שלא אמור להיות, נכון? על הנייר אז לא אמור להיות, אז מה? גם ב-FFT, אם אני עושה אף שלב זה נראה כמו FFT, אם אני לא עושה אבסולוט טוב, לא FFT זה שונה, אבל גם, מה? לא, נכון, ב-FFT כן, אבל אם אני בשום מקום ביקשת להראות כאילו יש חלק שצריך להראות שאני אינדקס UK במחליט של כמו שאמרת, זה לא כדי להיות הדבר.
שהחלק הנומרי,
אז מה, חלק חלק ממשי
אם היא 10 ומינוס 2,
לא, אבל יש לי איברים
אם היא 10 ומינוס 5,
כן, אבל יש לי איברים שבתוך יותר מאחד. ואני לא יודעת אם זה הייתי מדומם וגם
חשבתי לך אבל לא
משפיע על כל התדרים
משפיע על כולם.
משנה את כולם.
אבל נגיד
ההטלה של איזה
אבל נגיד עכשיו זה חלק לא משיק לי. כאילו נגיד בקונבולוציה, כאילו זה דבר הבסיסי לבדוק שזה יוצא אותו סיגנל. שאני חוזרת לטריל, ואם אני עושה את הפלוט, אני מקבלת אם אני עושה פלוט לטריל, אני מקבלת סינוס בפאזה שונה. שאני מניחה שהפאזה שונה, כי משהו עם העין. אבל שיחקתי עם זה, זה אפשר אולי לסדר, ומובנים ולעשות את זה במינוס, התחלתי את זה שומרים ב-UN. כאילו ניסיתי, חשבתי אולי כל הטעות שלי, עשיתי להם מבוססים.
בעיקרון, אם יואב אומרת
לא כאילו לעשות אתה לעשות לא דיגיטל וואי, כי אז אני ככה לא מפגש שלא הצלחתי כאילו להיכנס
אבל גם החלק הממשי הוא הגיוני שיש כאילו מספר של נשאר מורכב לבדוק
כאילו לשלטן הזה אבל זה לא משהו
אני יכולה להסתכל אם זה רק צריך להיות אולי אפשר לדבר ואם אני יש לי את הקוד פשוט על המחשב אם זה דווקא כן המטרה שלהם כן להתנסות ממש במשהו ממש כזה ולהבין כן, טיפה לשחק עם זה ולראות כאילו טיפה איזה
בוסט,
לדעת טיפה ובקטע הזה בכלל כאילו קצת דוגמא, אם זה לי הוא לא יודע אפילו להכתיב מוקד זה לא יוצא נכון כי כאילו מפחיד כפול אמרית זה לא יוצא לי
לא כאילו אני יוצא עוד
לא, זה ברגע שהגדלתי את אין מספיק ל-100 אני חושבת, או ל-140 כבר אמרתי לך, אם זה כפול אמרית זה לא יוצא אולי זה, אני צריכה לדעת כמה הבדל היה בטרייס היה מספר מורכב היה של חיים טוב, כאילו בא גם כדי להראות כל החיים רואים
חום באהבה
היא גם אומרת אני אוריך את הזבל
זה נשמע לי נכון בגדול אפשר להגיד מה שאתה עושה אם נתחיל אנשים יגידו את זה נכון
Okay. So, I'm starting now to talk about a new problem, a new topic, related still to what we've done so far. We've seen that from the point of view of the Infomax principle of encoding, when we had, say, a set of n inputs, multidimensional vector, it was useful to pick up the principal components of this vector. We've seen right now that there are also biological learning rules that can do that. Now, we know that the principal components of a Gaussian variable are uncorrelated, right? The statistics of the coefficient of these components are uncorrelated. And when we discuss Gaussian variables, there are also independent variables. So this suggests that this type of treatment of a multidimensional input might be useful not only from the point of view of coding, but also from the point of view of somehow separating an input which mixes various components into independent components. And this leads me to the problem that I'm going to discuss today and also tomorrow. By the way, tomorrow, because next week we will skip Tuesday because of the ISFN. We will have tomorrow 2 hours of class, of lesson, and no TA session, and we will have a TA session next week. So the problem that I'm going to discuss is the source separation problem. Sometimes called also the mixing problem. And I will start by just defining the problem. So we imagine that we have n sources which are generating some activities, real graded numbers, just some numbers Si. We assume that the SIs are drawn from independently of each other. Which means that the probability of a certain vector S can be written as a product over all the components Pi of Si for now. Let's imagine that these Pi's are known. They might be the same for all the sources. They might have a different structure, but for each source there's a certain probability. This is just the same as the inputs to, similar to the inputs that we discussed before. It's just some. Okay, so let me give you an intuition or some example. Suppose that several people here are talking at the same time, okay, and I have a microphone, and the microphone is recording the voice from these three people. So the source will be what the output of each person, and I will assume now that they're not communicating with each other, so they're independent. Each one of them is just talking independently of the others. So the microphone is picking up, but the microphone might be picking up the combination of what they're saying, which will be the next assumption in my definition of the problem. So the sources will be some sources generating something, but what I am observing is a set of n observations. Note that for simplicity, I'm assuming that there's the same number of sources and the same n observations. I will call the observations xi. And the xi's are going to be linearly related to the sources. So the vector x can be written as some matrix times the vector s. And this matrix is called the mixing matrix. And it's an n by n matrix. So going back to my example, I have a few people talking in the room, and my microphone, I have a microphone which picks up a linear combination of their vocal outputs with weights that depend on the distance of this microphone from these three people. I might have another microphone set up somewhere else in the room, and this microphone will have another set of weights because the distance of the other microphone from the three speakers will be different from the distance of the first microphone, and I can put in a third microphone. And you can imagine that if I have three speakers and I have three microphones, I have three sources, I have three observables, maybe I can invert this matrix, and given the observations x, find what were the sources. So under some conditions that's true. And the real question that we want to ask is whether there is some way to learn how to find that linear transformation that will recover the sources from the observations. Just for convenience. Okay. So up to now, what I defined so far is what is called the generative model for the x's. I told you how the x's are generated, right? You have the s's which are independent with some probability distribution. This goes through some linear transformation. And my goal is to find the sources, or at least to find the linear transformation that will recover the sources. So I will imagine that there are outputs y, which I'm trying to generate. They are related to the inputs by a matrix. And I want the y's to recover the sources. Okay? Now, in general, if I don't know, if I'm just presented with these x's, and suppose, for example, that all these pi's are the same, then in general, I might not be, I don't expect to be able to recover, to know which one of the inputs is which. So I will be satisfied if I find the y's which are a certain permutation of the x's. I don't care about the order. So maybe, so when I say find the sources, I mean up to a permutation. Sometimes I don't care also about the scaling. If my yi's are proportional to the si's, I'm already satisfied. Sometimes. But that's the goal. And obviously there is a solution. I mean, if this matrix is invertible, there is a solution, right? The solution is W equals A to minus 1, or W transpose is equal to A minus 1 transpose. It's the same. This will solve the problem if this matrix is invertible. Again, I'll be satisfied also if up to a permutation this is true. And but the real question is, suppose that you are presented with these x's. You're just presented with the x's, and you know something about these pi's. Is there an algorithm that will allow you to find a matrix that will separate the sources without knowing what was A? Of course, if I know what is A, it's a very easy problem. I just need to invert it. But suppose that I give you the outputs of the 3 microphones, and I don't tell you what are the distances of these microphones from the three speakers. Is there a way to find that optimal, a particular linear transformation that will separate the sources? Okay. So this is without knowing the A minus 1. Is there an algorithm that will find the appropriate W? That's the question. Now, the first very important observation that I'd like to make is that if the sources have Gaussian statistics, this problem cannot be solved. Okay? There is no way we can even hope to solve this problem. And I would like to give you an example to demonstrate why that's true. So imagine that we have 2 sources. These 2 sources are Gaussian. So 2 Gaussian sources. So if I would plot, let's imagine that everything is 0 mean, okay? So if I would plot the probability distribution of the first source, it will be a Gaussian. And if I would plot the probability distribution of the second source, it would also be a Gaussian. Okay? And now let's imagine that the matrix A transpose is the following matrix: 1, 0, 1, 1. Okay? So I have a 2-dimensional input, S1, S2, and I have a 2-dimensional output, X1, X2. And you can see that, remember that one column, I mean, S1 will affect X1 and X2 with these weights, and S2 will affect X1 and X2 with these weights. So if, for a moment, I would silence S2, I would make S2 0. The vector that I would get after applying A transpose will always have just a component X1. The X2 component would be 0. So if I would plot the distribution of the X's that I can get, that I will get just from the S1, now I'm plotting a 2-dimensional distribution, a distribution over S1 and S2. How would it look like? If I'm asking, suppose that we set S2 to 0, and I ask, what is the distribution of S1, S2 driven by S1? How will it look like? Okay, so in this plot, this is a kind of an intensity plot showing the probability to get a certain pair S1, S2. How would it look like? It will only be on this axis, right? Because S2 is always 0. So it will be some, it's hard to plot an intensity plot, right? But it will be some distributed over here and more intense here than here with a probability distribution. So, okay, let's do it like this. The probability will be along this line, and now I will just plot this line, which represents the fact that the probability to get a point here is higher than to get a point here and a point here. Do you understand what I'm drawing? Yes. Okay. Now, what happens if I look at the contribution coming from S2? The contribution coming from S2 this should have been x1 and x2. Sorry, x1 and x2, right? So x2 is all. If S1 is driving, if S2 is 0, x2 is always 0, and x1 is has a Gaussian distribution. And if I now silence S1 and ask what is S2 contributing to the vector x, well, how would it look like? So it's going to be a vector that has the same component x1 and component x2, right? Where will it be? Where will the probability be distributed in this two-dimensional? It's not a 2D Gaussian. It's still a line. It's still one vector. So it's x1 is always equal to x2. So the points where x1 is equal to x2 are along this line, right? So I'll get a distribution along this line again with some Gaussian distribution of the intensities, something like this, right? Now, the true x is a sum of the contribution from S1 and the contribution from x2. Oops. So if I would plot now the scatter, an intensity plot of the joint probability of the probability distribution of x1 and x2, when both S1 and S2 are active, but they're independent, now we'll get a sum of these vectors plus these vectors. So if I ask what is P of x, this is x1 and x2, this will be some cloud that will look like this. Okay, if I plot the contour plots of this, if I plot the contour plots of this probability distribution, they will look like this. And it's a Gaussian distribution because a linear combination of Gaussian variables is always a Gaussian variable. So this is a two-dimensional Gaussian distribution, and it looks like this. The motion along this direction is driven both by S1 and S2. The position along this direction is driven only by S2. Now I claim that I know of a very easy way to project these values x1 and x2 to linearly transform these values x1 and x2 such that I will get two independent numbers. What is that? What is the most simple idea that comes to mind? To take the principal components of this distribution. What are the principal components of this distribution? They are along this direction and this direction. So I found a way to generate two imagined sources which are independent of each other, but they're not the true sources, right? The true sources are not this will not give me S1 and S2. It will give me some combination of S1 and S2. Okay, so the fundamental reason for this is that Gaussian variables, a multidimensional Gaussian distribution, there is more than one way to generate, to linearly transform it in order to get independent components. One is to project over the principal components. But there are other ways. Remember that once we project it over the principal components, we can squash this direction such that we'll get a spherically symmetric distribution. And then we can do any rotation that we want, and we will still be left with uncorrelated independent variables. One of these, and then we can squash or expand one of the new directions. And one of these choices will give the true S1 and S2. But I can't tell. I can't say which combination is the correct one. So all this was just a demonstration that if the inputs are Gaussian, it's hopeless to solve the mixing problem. There's no criterion that I can apply that will tell me what is the correct linear transformation. There are many possible solutions. However, turns out that the mixing problem is solvable in general. Just a second, I'll just write down and then I'll answer. Question? Yes. Lior? Okay. So, first of all, you're asking about this and this, or this and this? I mean, the connection between... Yes? To this? Okay. So again, what I showed here is the distribution of the x's that are generated by by S1. This is clear, I think, yes? And this is the distribution of the x's that are generated by the S2. But the true x is the sum over these two. It's the sum of the points that are generated here and the points that are generated here, and importantly, they are drawn independently of each other. So what happens if at each step I draw one of these points and I add to it as a vector one of these points? I will get a vector which is distributed in the two-dimensional space like this. Okay, so imagine I choose this. I might, for example, at one particular step happen to choose this point. Okay, to choose this point here, and at this point, and here choose this point. So the end up, let's choose this point. So the vector that I will end up with will be this plus this. It will be here. Imagine that you repeat this many, many times. You will get a distribution of points x that will have this two-dimensional Gaussian distribution. Does it make sense? Yes. Yes. And it's important to recall that this two-dimensional distribution is a two-dimensional Gaussian distribution. This is simply because of the property of Gaussian distribution that a linear combination of Gaussian variables is a Gaussian variable. And therefore, I also know that it has this, every Gaussian distribution looks like this. The contour plot, the contour lines has the structure of these ellipses, but the direction and shape of that I chose depended on what I assumed here. Okay. Well, the point is that the only goal that we can hope to use is that we want our sources to be independent of each other, right? Now, what I'm saying is, here's a way to choose to project on these I can rotate to these two principal directions and generate two numbers that will be independent of each other. So this seems like a good solution to the problem, but in fact, it's not the original. These will not be the original sources. Okay, the original sources, for example, S1 is simply equal to X1. So I should have projected, actually, if I wanted the original S's, I should have projected like this to the X, not projected in this direction, in this direction. So I found a linear transformation that gives me two independent numbers, statistically independent numbers, but these are not the two numbers that were really the sources, S1 and S2. And in fact, there are many, many different linear transformations that will generate two independent numbers, and there is no criterion that I can use in order to identify which is the correct one. Okay? Now the next... Yes?
How is it different than other probabilistic distributions?
This is what we're going to discuss now. So this is really something special which is happening with Gaussian distributions. And the next statement that I wrote here on the board, which I will need to motivate, is that the mixing problem can be solved typically if the sources are non-Gaussian. Okay?
That's a property of the Gaussian distribution?
Yes, it's really because of the property of Gaussian distributions that any mixture of Gaussians is also a Gaussian. And what we're going to use, the next thing that I want to do is to motivate this. I'm not going to show it, but I'm going to give you some intuition why it's true that when the sources are not Gaussian, you can solve the problem. And the reason is, let me first say it in a kind of very, very qualitatively, that if you mix sources which are non-Gaussian, you typically get something which is more Gaussian than the sources. Okay? So, okay, well, you'll see where this leads. So, first of all, where would we know of an example for this? One thing that you probably know, is the central limit theorem. Okay, so first of all, what I'm doing now is motivating or giving you some intuition for this statement. And let me start by mentioning the central limit theorem. The central limit theorem tells us that if you sum many independent variables, which might have a very non-Gaussian distribution, each one of them, but they're drawn independently, you end up with a Gaussian variable, right? So this is suggesting that when we combine variables which are non-Gaussian, we get something which is more Gaussian, which is a Gaussian. So it turns out that similarly, a finite, so this is really true in the strict limit that we take many, many variables and sum them up. But even for a finite linear mixture of independent variables, usually it's usually more Gaussian than the individual contributions. Now, what I wrote here really deserves some discussion. What do I mean by usually, and what do I mean, especially what do I mean by more Gaussian, right? So we'll need to talk about that. But I first want you to get the intuition. No. So now I'll explain. So that statement is that if you have sources which are non-Gaussian and you mix them, you get something which is more Gaussian. And that suggests a way to solve the demixing problem. We might want to find a linear transformation over the of the observations. So if the observations are a linear mixture of the sources, the observations are more Gaussian than the sources. That's what we hope. And therefore, we might look for a transformation of the sources, a transformation of the sources of the observations that will generate something which is less Gaussian than the observations, because the sources have to be less Gaussian than the mixture of them. So one way to approach the mixing problem, we will talk about this in more detail later, is to look for a linear transformation of the observations which generates numbers which are less Gaussian than the observations. Again, the idea is that the observations are more Gaussian than the sources because they are a linear mixture of them. Yes, this needs discussion. Okay, but so what do I mean by more Gaussian and less Gaussian? And let me first, before I try to quantify it using some numbers, I want to give you some intuition why it's the case that this statement is true. So I just want to give you some examples. Imagine, for example, that S1 is generated by some distribution which is kind of more peaked than a Gaussian. Okay? Something like this. So this would be P of S1. And imagine that S2, which I will draw here, has also a distribution of this form. This would be P of S2. If I would draw the joint distribution of S1 and S2, how would it look like? If I would draw the contour lines of this distribution, the lines over which the joint distribution is constant, it will look something like this. Okay, and this will be another contour line, and this will be another contour line. Now, you can try to do it yourself on a computer. You can ask, suppose that I project over on some particular direction. So I generate, projection on the direction is like generating a linear combination of S1 and S2. Of course, if I choose my direction like this, I will get S1. So I know what the probability distribution looks like. It looks like this. If I take the linear combination that generates S2, I will get this probability distribution. Turns out that if you take something like S1 over, plus S2, this is like projecting over this line, because this is the line over which S1 and S2, I mean, on each line like this, sorry, no, it will be something like projecting over something like this. On each line like this, S1 and S2 are constant. So I need to ask where, if I project over this line, where do I fall? Turns out that if you would play this game and look at the probability distribution of a projection on this direction, a linear combination like S1 and S2, it will look more Gaussian than, less peaked than these probability distributions. But so S1 plus, this will be P of S1 plus S2. Okay? And it turns out that if you would do it a projection on different directions, I still didn't define what I mean by more Gaussian and less Gaussian, so I'm just telling you that by eye it will look like this. If you will choose a direction like this, which is a mixture of the two S's, it will look more Gaussian than the probability distribution that we get if you choose one of the S's. So as a function of the angle that I choose, I will get the most Gaussian distribution in this case when I choose to mix S1 and S2 with the same coefficients, and if I just choose one of them, I get something less Gaussian. Let me give you another example, which is even a little bit easier to visualize. Okay, I think that I will need more space, so I will do it. I will do it here. The second example will be an example where the distribution of S1 is less peaked than a Gaussian distribution. It will be just a uniform distribution. This will be P of S1. This will be P of S2. Okay, and therefore, if I ask what is the joint distribution of S1 and S2, how does it look like? Or constant where? Over a square, right? The joint distribution, so let me use the same color as here. The joint distribution will be just a uniform distribution over this square. This will be P of S1 and S2. Now, imagine that I look at the probability distribution simply of S1, I will get this distribution. If I look at the probability distribution of S2, I will get this distribution. What happens if I look at the probability distribution of S1 plus S2? So S1 plus S2 is constant along lines that looks like this, right? This is one line like this. This is another line. This is another line. So if I look at S1 plus S2, it's like projecting over this direction. What will be the probability of S1 plus S2? So if S1 plus S2 is 0, I will get contribution from all these points along the diagonal, right? But if S plus S2 is larger or smaller, I'll get a contribution from a smaller number of points, right? So it will end up looking precisely like this. This will be the probability distribution of S1 and S2. And in a very crude manner, you can say that this looks more like a Gaussian than this, right? Okay. Now, after this kind of hand-waving and just simple intuition, I want to discuss in more precise terms how can we quantify Gaussianity or non-Gaussianity. So this is a somewhat technical part. It's easy, but it's mathematical and technical, but we need to do it. And after we do it, we'll go back to discuss the mixing problem. So what I'm going to discuss now is how can we quantifying non-Gaussianity. And another possible title for this part is the concept of cumulants. Okay, so imagine that we have some particular probability distribution, P of x, the probability distribution. We can define the moments of this distribution. Many of you probably encountered this definition. The nth moment of the probability distribution is defined as the average of x to the power of n, which can also be written as an integral from minus infinity to infinity, x to the n, p of x dx. So mu n is the nth moment of this probability distribution. And in particular, mu 0 is, what is mu 0? It's 1, right? Because the integral of 1 times p of x dx is 1, p of x is normalized. So mu 0 is always 1. Mu 1 is the average of x. Mu 2 is the average of x squared, and so on. Now, it's convenient to define a function which is a function of a different variable. It's a function of a variable that I will call t. And this function is defined by the fact that the coefficients of the Taylor expansion of this function around 0 are the moments of this distribution. So it's defined by the fact that it can be written as mu 0 plus mu 1 t plus mu 2 t squared over 2 prime plus mu n squared, mu n t to the n of divided by n factorial, okay? And this function is called the generating function of the moments. Again, it's a mathematical construct. It's a function whose Taylor expansion coefficients are equal to the moments of this distribution. But I claim that we can rewrite it. We can write exactly what it is in a more simple terms. Let's do this. So f of t is equal I'm going to use now the definitions of the moments. Okay, so it's equal to an integral from minus infinity to infinity, p of x, times, for mu 0, I need to write 1. Here, I need to write mu 1 times t. So mu 1 is the average of x. This is multiplied by t, so I'll have here x times t. When I do the integration, at the end I will have dx. When I do the integration over x, it will generate the first moment times t. So this term is okay. For the next term, I will write here x squared t squared divided by 2 factorial. If I will do the integration over x, p of x, x squared will generate mu 2, and I will be left with mu 2 t squared over 2, so that's fine, and so on. So this is just another way to write f. But now, what is this? One times xt plus xt squared divided by 2 factorial plus xt to the third divided by 3 factorial. It's the exponent of xt. This is the exponent of xt. And therefore, what you see is that f of t is equal to the integral of p of x, exponent of xt dx, which is nothing but the average of e to the xt, averaged over x. Okay? So f of t, the generating function of the moments, can be written as a function of t. It can be written as an average of e to the xt. Okay, you're beginning to wonder why am I telling you all this, but you will see soon. So now I'm going to define another function, which I will call, so it's another definition. I will define another function, g of t, which will be defined as the log of f of t, or in other words, the log of the average of e to the xt. And just as much as I could express this function as this is a function of t, right? I can express it as a Taylor expansion around 0 with these coefficients. I could ask, what is the Taylor expansion of g of t? So I could Taylor expand g of t and write it as kappa 0 plus kappa 1 plus kappa 1 t plus kappa 2. This is by definition, kappa 2 t squared over 2 factorial and so on. And I'm out of space here, so continue here. Okay, so kappa I are called, this is a name, it's a definition, are called the cumulants of the probability distribution. So again, the moments were defined here, and I can view them as the coefficients of the Taylor expansion of f of t. I constructed this thing that I called, function that I called g of t. I expanded to Taylor expansion. I call these coefficients the cumulants. They depend on the probability distribution of x. And therefore, g of t is called the generating function of the cumulants. Okay. Now, there is a one-to-one relationship between the moments, these coefficients, mu 0, mu 1, mu 2, and so on, and the cumulants, kappa 0, kappa 1, kappa 2. I will not derive this relationship right now. I will just tell you that if you work this out, you find that kappa 1 is equal to mu 1. I'm not writing kappa 0. Kappa 2 is equal to mu2 minus mu1 square. This, by the way, has another name. Mu2 is the average of x squared, and mu1 is the average of x. So what is this? So this is the variance, and so on. One can write expressions for the kappa i's in terms of the mu i's. And next, look up in Wikipedia and you'll find the list. Kappa 3 is some complicated combination.
Okay, but it's complicated. It's not like
It's well, the one thing is that each kappa depends only on the moments up to that order. Okay, that's important. I will write a somewhat longer list right now after making an assumption. So.